everybody. There's the usual attendance form. Cameron, I like your picture. I don't think I've seen that one before. It's pretty fun. I like everyone's pictures, but there's a new one. Enjoying it. Let me pin my video here. Okay. All right, so let's see. Let me think for 1 second. I know that Carlson's class has a test today. Is that correct? Yeah, it's like, I don't know, I'm not in this class. Well, if you're in, yeah, okay, yes. Hopefully it isn't too impossible. I will admit the practice exam looked challenging and not like what I would want to be testing you guys on, but I'm not the teacher, so it's not up to me. Are there any, so I guess to the Carlson students first, are there any questions that you might want me to address? I don't actually have a copy of the exam. I don't know if you guys have it yet, but if there's anything you would like me to talk about, not specifically answering a test question, but looking at something similar maybe, if you have something, now is your chance to kind of speak out. Otherwise, I've got lots of other things we can look at for everyone. Felicity's out and about. It's exciting. All right, well, not hearing from anyone in Carlson's class, which is fine. Again, feel free to shoot me an email later. Excuse me. Oh, man, excuse me. I don't know what the time frame for taking you guys' tests looks like, so I don't know if you have just like a couple hours or a whole day or what, but if you're in Carlson's class and you have questions, you want to send me a message or start a discussion on Canvas, please feel free. I'm happy to help in whatever ways that feel ethically correct. Let's see, what about everybody else? I know that Cimental or Rodriguez's class is talking about double integrals. I don't know where Rademacher's class is right now because you guys just had a test. I imagine you're moving into talking about systems of linear differential equations, but I don't actually know for sure. So you guys have any questions?
Could we do the material that you think we'll be covering soon enough?
Sure. So we have a mild issue in that I'm guessing Rademacher isn't really covering double integrals. So just 1 second, actually. Yeah, can you turn down a little bit? Okay. So I feel like we should talk a little bit about double integrals because it is something that some people are going to have to look at, but it's not something that everyone has to do. So let's spend a little bit of time today talking about double integrals, and then we can continue on our path of where everyone should end up soon, which is talking about differential equations. Let me grab my integral examples here. Yeah. Okay. And I don't want to get, sure. He actually, I feel like, so I was watching his class today, and I think he did a good job of talking about how to do a double integral when the limits of integration are other than just constants. So we'll do a couple examples, and then we'll try and move on. Let's do something like this. So here's an interval. So interval from -1 to 2, and then interval from 0 to 3 of 6 minus 2x minus 4y dx dy, meaning we're first integrating with respect to x, and then after that we're integrating with respect to y. When I read that, I kind of, what's the thing I want to say? It makes me know that my inner limits of integration, this is x equals 0 to x equals 3, and then the outer limits are y equals 0 to y equals 2. So if I was asked to draw the region that we were integrating over, I would know that, okay, x is going from 0 to 3, y is going from -1 to 2. So this is my region. And whenever your limits of integration are all constants, your region is always going to be a rectangle. This one happens to be a square because of the same width, but you know, and then integrating something like this is fairly straightforward. You integrate with respect to that variable first, or fist. Let's try that again. First, and you do that one second. So if I'm integrating this, I'm going to get the -1 to 2. And I'm going to anti-differentiate this with respect to x. So just like when you differentiate with respect to x, you treat all the non-x things like constants. The same is true when you integrate with respect to x. So if 6 integrated with respect to x is 6x, -2x becomes -x squared, and -4y, that's just a constant, so its integral or antiderivative is -4y times x. From 0 to 3, dy. And again, that's x equals 0 and x equals 3, so we're going to plug in 3 for x, subtract and plug in 0 for x. This is going to equal still the integral from -1 to 2. Plugging in 3 for x, I get 6 times 3 minus 3 squared minus 4 times y times 3, which is 12y. And then minus, I would plug in 0, but that's going to be 0, that's going to be 0, and that's going to be 0, so it's all 0, so I'm not going to bother. And then it's just like a regular integral. So I'm going to go ahead and anti-differentiate. Again, get 18y. I guess I could put these together. Right? 18 minus 9 is 9. So I'm going to get 9y minus 12y squared over 2, or 6y squared, from -1 to 2. And I'm just going to plug it again. So I'm going to plug in 2. We get 9 times 2 minus 6 times 2 squared. Minus, I'm going to plug in -1. We get 9 times -1 minus 6 times -1 squared. So I end up with, let's see, -6 minus -15. So I end up with -6 plus 15, which is 9. So that's how something like that works. And it's usually pretty straightforward when your limits of integration are constants like this, right? It's not too terrible. Things get more challenging when you have limits of integration that are not like that. So how do I want to phrase this? Yeah, let's do it this way. Sure. So let's look at this double integral. You know, from 0 to 1, you know, from the square root of y to 1 of This is a great example of a double integral because it's impossible to do as it's written. This can't be integrated. There's no way to anti-differentiate the square root of x cubed plus 1. There are lots of examples of functions. So like here are 3 functions. There's 3 functions that don't have antiderivatives, at least not in the general way we think about them. And so when you see something like this, the whole point is that you have to change the order of integration. But you can't just change things like, so really the whole point is you have to draw a picture. So I'm going to draw the region. And now, it's funny because the way Rodriguez was saying today is kind of the opposite way that I think of it, but I think his description was very good. So the way he talked about it was, you're fixing the outer one. So y is fixed between 0 and 1, because these are the y limits. Right? The outsides go together. And then the x limits are bounded between this x equal to the square root of y and x equal to 1. This is kind of actually backwards from how you might start usually. So our job here is to draw this picture. I never start with this. I always start with this. So I'm going to draw x equal to the square root of y, also known as y equal to x squared. But it's only the right-hand half of it because the square root of y is only ever positive. So x can only be positive here. So here's my, I've done that better in the past. Here's my x equal to the square root of y function. And I've also got x equal to 1, which is a vertical line. So what I'm thinking about is my x values are bounded between x equal to the square root of y and x equal to 1. And x moves from left to right, so it's a horizontal strip that's bounded by these two functions. And then the strip is allowed to move as far down as y equals 0 and as far up as y equals 1. So that's the way I envision this happening. Whereas I think Rodriguez says, you know, if you're trying to figure out how to write this in terms of limits of integration, he's thinking about y being fixed from 0 to 1, and then x has to be between these two functions. Still the same idea, just kind of backwards behind it, which is fine. But the point here is that you actually have to take this and you have to re-express it in terms of the other order of integration. So what we're going to do is we're going to draw this picture again. And so the way I kind of really envision it is instead of using a horizontal strip, where I'm using a vertical strip. And the way Rodriguez is talking about it is he's talking about the vertical strip being fixed between 0 and 1. And now it's x equals 0 to x equals 1. Right, that's the point 1, 1. And then the y values are between y equals 0 and this function here, which is y equals to x squared. So now I can rewrite this integral as, instead of dx dy, it's going to be dy dx. The y's go from y equals 0 to y equals x squared. And the x's now just go, well, this strip can go as far left as 0, as far right as 1. And the point of this now is that now we can at least do the first step for integration because there's no y's in here. So I can integrate this with respect to y because that's just a constant as far as y is concerned. Now look what happens. Let's go ahead and go to the other side of the board here. A couple things to know, just in general, about double integration. The outer limits of integration should always be constants. The inner limits of integration can be variables, but they can also be constants. And whatever variable is here is not the variable you're integrating with respect to, right? I have x's here because I'm integrating with respect to y. Just like I had y's here because I was integrating with respect to x. So these should always be not the same, right? If you're integrating with respect to x, it's because x is equal to something. If you're integrating with respect to y, it's because y is equal to something. So good tips to remember. So now here's the deal. This is super easy to integrate with respect to y. It's just y times the square root of x cubed plus 1. from 0 to x squared. And now we're going to plug in the limits of integration. And we're going to get, oh, sorry, I didn't give you guys, did I give you guys the attendance form? I did, okay. Good. Okay. So then we're going to plug in y equal to x squared. And then we would plug in y equal to 0, but we get 0 times whatever, which is just 0. And now, this is a u substitution problem. So this happens a lot. You do the integral with respect to the first variable, and then you get something that is easy to integrate after you plugged in whatever your limits are. So now we could do, oh yeah, u is equal to x squared, du is 2x. Oh, that's not right. U is not equal to x squared. I mean, right? I don't pick that. I pick this because 1, it's inside the function. 2, its derivative is essentially x squared. So I pick u equal to x cubed plus 1. Du dx is 3x squared. Du over 3 is x squared dx. And I definitely have an x squared times dx. So this integral is going to equal du over 3, so 1/3 du, integral of the square root of u. And personally, I prefer to change my limits of integration when doing a u substitution. So instead of writing x equals 0 and x equals 1, I'm going to say, well, if x is 0, u is 0 plus 1, which is 1. If x is 1, u is 1 cubed plus 1, which is 2. Then I don't have to change back after that, which is nice, I think. So let's see, this is u to the 1/2. The integral of u to the 1/2 is u to the 3/2 divided by 3/2, which is times 2/3 from 1 to 2. That's going to be 2/9 times plug in 2, it's not pretty, minus plug in 1. 1 to any power is 1. And that's as good as our answer gets, actually. If I could rewrite this problem, yeah, I feel like it's a big oversight. Let me look at one thing real quick here. Yeah, that's too bad. The person writing this problem should have made this a 2. Because this, sorry. Yeah, if this was a 2, then 2 cubed plus 1 would have been a 9. And then 9 to the 3/2 is way nicer, it's 27. So someone could have made this problem a lot nicer with one little change. But that's not the point. The point is this is how you did the problem. There are questions about this.
I'm still confused on how you change the integral.
The order of integration?
Yes, the order of integration.
Sure. So let's look at another example here. And so I will say the general answer to that question, Teresa, is by drawing a picture.
Okay.
So, but I mean, no, it's kind of the only way. Is it the only way? So I should say, if the limits of integration are constants, you can change them without doing any work.
Okay.
But if they're not constants, then you have to draw the picture. So let's do another one. Let me think for a second. If I have anything good, I must need. I want to see if I can pick a nice. Oh, that's the wrong page there. One second. I had one lined up. Now I've lost it. No, not you. Sure. Let's look at this one. Let's do the integral from 0 to 2, and then from, what have I got here? Where'd you go? Sorry. I had it. Sorry. Yeah, let's do that. X squared to 2x of x cubed plus 3y squared. Divide this. Now, I will fully admit there is no reason to change the order on this one. You could totally do this one as is and be perfectly fine. In fact, let's go ahead and do it as is just to see what we get. So integrating this, the antiderivative of all this with respect to y, I'm going to get x cubed y plus y cubed from x squared to 2x. We're going to plug these in. It's going to get a little bit messy. So plugging in y equal to 2x, I'm going to get x cubed times 2x, just 2x to the fourth. Plugging in 2x for y there, 2x quantity cubed is going to be 8x cubed minus, now we're plugging in the bottom one, x cubed times x squared is x to the fifth, and x squared cubed is x to the sixth. Okay. Integrating the rest of this, so I'm going to get 2x to the fifth over 5 plus 8x to the fourth over 4 is just 2x to the fourth minus x to the sixth over 6 plus x to the, sorry, minus, right, because that distributes. Eraser, keep it together. X to the 7th over 7. Plug in 2, it's going to get kind of gross. So let's see, we get 2 times 2 to the 5th, which is 64 over 5, plus 2 times 2 to the 4th is 32, minus 2 to the 6th is 64 over 6, 2 to the 7th is 128 over 7. That's something. I don't care to finish what that is. I'm sure we could if we really, really wanted to. Well, let's go ahead and see what it looks like when we change it around. So, I'm sorry. And so if I'm changing things around, to me it always feels better to draw the inner limits. So I'm going to draw y equals x squared and y equals 2x. And since I know that those cross each other, I should probably see where they cross each other. So x squared equals 2x, x squared minus 2x equals 0, x times x minus 2 equals 0. Not surprisingly, we actually end up getting these values. That happens a lot, is that you're integrating over the region where they've intersected. So y equals x squared looks like this. And y equals 2x looks like this. So here's my region in between these two functions. And what we were doing before is we were saying, okay, I've got a vertical strip. I'm going from y equals x squared to y equals 2x. And then as far left as, color here. We're going as far left as 0 and as far right as 2. But you know, when we go further right, the strip isn't like this anymore. It's, you know, it's up here like this. When we go to the left, it's down here like this. So the vertical strip is still between those two functions. Now what we're going to do is we're going to envision using a horizontal strip. Or as your professor might say it, he would say now the y values are going to be fixed between 0 and 4. This is the point 2, 4. And the x's are going to be between two functions. So the y values are going to be between 0 and 4. I should do it in green. And the x values are going to be between these two functions. So the x values are between the right function and the left function. Where you're writing x as a function of y. So looking at my picture, this is one of the reasons you look at the picture. The right function is y equals x squared. So that's y equals x squared, which becomes x equal to the square root of y. The left function is y equals 2x, which becomes x equal to y over 2. So here's what the setup for this integral would look like after we change the order of integration. You would have y going from 0 to 4, and then the horizontal strips in between are bounded on the lower side, the left side, by x equal to y over 2, and the upper or right side by x equal to the square root of y. And that's what that would look like. And then integrating would be a little bit different, right? We would first integrate with respect to x. So we would get x to the 4th over 4. Sorry, the integral from y equals 0 to 4 of x to the 4th over 4 plus 3y squared x from y over 2 to the square root of y. And then it's going to get pretty messy. Right? You definitely would want to do this problem the first way it was written, like changing the limits of integration here doesn't really make a lot of sense. But you still could. And then you plug this in. I'm going to erase my picture now. And then plugging it in, the square root of y to the 4th is just y squared. So you can y squared over 4. Y squared times the square root of y is y to the 5 halves. Then you're going to plug in y over 2. Y over 2 to the 4th is y to the 4th over 16 over 4 is 64. That looks worrisome. Oh, well, that's life. Yeah, that seems weird. Anyway, plugging in y over 2 for x here, you get 3y cubed over 2. Yeah, gross. From 0, not from 0 to 4. And then you have to integrate, right? So then you'll integrate this, you'll get y cubed over 12 plus 3y to the 7 halves times 2 sevenths minus y to the 5th over 5 times 64. Minus 3y to the 4th over 2 times 4. So that's pretty gross. Plugging in, yeah, plugging in 4, you get 64 over 12. This is 6 sevenths. 4 to the 7 halves is 2 to the 7th, which is 128. The point is not to be doing this. I should stop, really. Anyway, you can finish this off if you want to. I don't think you really need to, but you can see that this is going to be the same as this. I mean, it might not look like it yet, but it's going to be the same. Let's look at one more thing. So let's see. Here's what I want you guys to try. Let me think for 1 second here. So I would like you to, sorry, let me think. No, sorry. All right, I want you to rewrite this integral. So it's the integral from 0 to 4 of the integral from x to 4 of e to the y squared dy dx. And just so you all know, this integral is impossible as it's written. We cannot anti-differentiate e to the y squared with respect to y right off the bat. So I want you to rewrite this. So what you really need to do is you draw this region and then flip things around. So go ahead and try that. I'll start doing it slowly, but I want to give you guys a chance to work on it on your own. So this is how I imagine the integral as it's the region as it's currently written. The region is being expressed as the bottom boundary is y equals x and the upper boundary is y equals 4. And then that vertical strip can move as far left as x equals 0 and as far right as x equals 4. But now I'm going to switch that. So I'm going to do here. So I'm going to draw a horizontal strip where now the right-hand boundary of the strip is y equals x, or x equals y. And the left-hand boundary is x equals 0. And then the strip can slide up and down instead of left and right. It can slide as far up as y equals 4, and it can slide as far down as y equals 0. So when you're talking about the sliding of the strip, it's always sliding between constant numbers, right? The strip is sliding up or down to whatever maximum or minimum height it is, or sliding left and right to whatever maximum or minimum values you can get to. Whereas the boundaries of the strip, those are the things that might be functional in nature, right? The bottom of this strip here depends on how far left or right we are, so it's going to depend on what x is. That's why the bottom of the boundary is y equal to x. The smaller x is, the lower the boundary goes. The higher x is, the higher the boundary goes. Same deal for this one here. So we're going to rewrite this as, so we said y was going from 0 to 4. And we said x is going from x equals 0 to x equals y. Same thing. And now it's dx dy. And then you can totally integrate this, right? You're going to get, sorry, my 4s and my y's kind of look the same. You can go from 0 to 4. Then you're going to e to the y squared dx is just x times e to the y squared. From 0 to y dy. And then you would plug in y for x. You can go from 0 to 4 of y e to the y squared minus 0 times e to the y squared is 0. And then the rest of this is very straightforward. You could do a u sub for u equal to y squared. Here's what you're going to get. You're going to get 1/2 e to the y squared as your antiderivative. Because the derivative of e to the y squared is e to the y squared times 2y. The 2's cancel, and the derivative of this is exactly y times e to the y squared. And you plug in 4, you get 1/2 e to the 16th power minus, you plug in 0, you get 1/2 e to the 0th. So that's how you do a problem like this. Let's see one thing here.
Wait, James. So
Yeah.
you said that when we were switching the order of integration, you said that the boundaries, they can be the functions, but when we're sliding from like up and down or left to right, that has to be constants.
Correct. So the way I'm envisioning it is, so here's the thing, right? I'm drawing a strip, and the orientation of the strip determines kind of which way you're integrating. So with the vertical strip, you're doing dy dx.
Mm-hmm.
Inner limits are you saying, oh, y is bounded by this boundary and this boundary. So you're going from y equals x to y equals 4. And then the outer limits are just how far left and right you can go, the strip.
Mm.
Whereas the other way here, I was doing a horizontal strip. When it's a horizontal strip, you're always going to have a dx first and a dy second.
Oh, yeah.
And so when I think of that, I think, oh, dx first, so the x's are the boundaries. And this horizontal strip is bounded on the right by this function x equals y, and bounded on the left by this function x equals 0. And then I can think about this horizontal strip being able to slide up to the tallest place of 4 and down to the smallest place of 0. So yeah, I was thinking about the sliding between constant values, but the boundaries of the strip, either the top and bottom of the strip, if it's vertical, or the right side and the left side of the strip, if it's horizontal, those boundaries are the functions. Which, if it's a rectangle, are all just numbers. But if it's something that's different than a rectangle, like a triangle or something else, it's not going to be numbers. It's going to be functions. Let's see. Oh, wow. Okay. Sorry, I was looking at Rodemacher's notes here real quick. Looks like he's really. Sorry, hold on. You're still open. Okay. Sorry, just one minute, please. Okay. So hopefully that gives those of you that need a good idea of what's going on with double integration. If you want, I can make a couple short videos that those of you that want to watch them, you can see them. But if you want, if you're interested in that, maybe send me an email or start a discussion letting me know what kinds of examples you want to see so I can more specifically do that for you guys. But let's take a look here at, yeah. So Rademacher has really kind of gotten well into chapter 10, it looks like, at least from the notes I'm looking at on one note. He's talking about equilibria and stability in linear systems of differential equations. So we should probably try to catch up to that because, well, it's important. So let me make up something that might not be wonderful, but okay. Let's say we have this system of linear differential equations. I'll do that, sure, that'll be fun. Sure. Okay. And I wrote the 2x2 over here because I didn't want to write this x1 here, but something people do actually write the 0x1 there. There's my system of linear differential equations. And what I want to point out, for most of these systems of linear differential equations, I think for all of them, 0, 0 is an equilibrium point, right? If x1 equals 0 and x2 equals 0, then the derivative is 0. Meaning, right, if I plug in the 0 for x1 and 0 for x2, dx1 dt is going to equal 0. And dx2 dt is going to equal 0. And if both the derivatives are 0, it means things aren't changing. And if things aren't changing, that's an equilibrium point. So if you can find places where both derivatives are zeros, or 0, you're finding a place that's a point of equilibrium. Now, we're not yet there at determining whether it's a stable or unstable equilibrium point, but that's something we're going to be doing. But right this minute, we're just trying to find where you have equilibrium. So here 0, 0 would be actually the only one. And I'm actually trying to remember in my head how we actually find the equilibrium points. Fine. Must know everything on the top of your head, right? But so, actually, yeah, how do we find equilibrium points? I don't know. But let's not worry so much about that right now. Let's solve this. So what I really want to do is I want to find the eigenvalues and the eigenvectors. And this one I feel like is kind of special. Maybe not that special, but it's a little bit special. So here is our differential equation. We've got dx1 dt, dx2 dt equal to the matrix of coefficients times the variables x1, x2. And now I want to find the eigenvalues and eigenvectors for this matrix. So eigenvalues. So again, we're going to do this. We're going to do the determinant of our matrix minus lambda times the identity matrix. Again, I'm really just putting minus lambda into the diagonals. So I get 4 minus lambda, 3, 0, and 2 minus lambda. We're going to set that equal to 0. Now, there's actually a question on the quiz I wrote for you guys kind of related to this, but I'll point it out here. It doesn't really matter. So I take the determinant of this, I get this times this minus this times this. And normally I would multiply this out, except that 3 times 0 is just 0. And I don't really need to, in fact, it's counterproductive to multiply this out if I'm trying to figure out what the solutions are. It's better just to leave it factored. Now I've got 4 minus lambda times 2 minus lambda equal to 0. So what are my eigenvalues? Exactly, right? Now, there is a way, so, now I'll let you guys, there's a way you can look at the matrix and know the eigenvalues if it's a special kind of matrix, which I'll talk about on class on Wednesday, I guess. But I think you guys can probably figure it out on your own and really, really, really trying not to just give it away. So there are some kinds of matrices you can just look at and know the eigenvalues right off the bat. Not every matrix, but some matrices. So our matrix was 4, 3, 0, 2. Our eigenvalues were 4 and 2. And now we're just going to find the eigenvectors. So typically when I'm doing this, I name my eigenvalues. I'm going to call one of them lambda 1 and one of them lambda 2. It does not matter which way you name them as long as you're consistent. But the reason I do that is so that I can know which eigenvalue goes with which eigenvector. So for lambda 1 equal to 1, sorry, for lambda 1 equal to 4, we're going to find the eigenvector v1 by doing this. A times v1, which we'll call x, y, and that's my v1, is equal to the eigenvalue, 4. v1. Now look what happens. I get the equation 4 times x plus 3 times y equals 4 times x. Now what? Well, those cancel. So I get 3y equal to 0, so I get y equal to 0. Normally that'd be enough to stop there, but I want to make sure you guys really understand why that's enough. So let's go ahead and look at the other equation real quick. We do the other equation, I get 0x plus 2y that equal to 4y. I'm still going to get y equal to 0, right? Because this is nothing. I get 0 equal to 4y minus 2y is 2y, divided by 2. So great, y equals 0, but what's x? Exactly. So here's a couple things to know. An eigenvector can be any vector except the 0 vector. So x, if you get y equals 0, but you don't get a condition on x, it means x can be anything except for 0, because you can't have 0, 0. So choose anything you want for x. What do you think I'm going to choose? Exactly, right? So I was like kind of off camera because I'm trying to be out of the board. I'm going to choose 1 because I'm going to choose the smallest positive integer I can. So I'm going to choose x equal to 1. My eigenvector is going to be 1, 0. But you could have chosen 2 or -3 or 1,000, and that's also an eigenvector. Because once you have an eigenvector, any multiple of it is also I should say, any non-zero multiple of it is also an eigenvector. So if that's an eigenvector, so is 200, 0. That would also be an eigenvector. And the reason why is because they both solve this equation. If I'm looking at this, 4302 times 1, 0 is going to give me, let's see, 4 times 1 plus 3 times 0. 0 times 1 plus 2 times 0. And that's exactly 4 times my eigenvector. But it also would have worked if I picked literally any other multiple that wasn't 0. I could have done 200, 0. And let's see, 4 times 200 is 800. Sorry, 800 plus 3 times 0 is 0. And 0 times that plus 2 times 0 is also 0. And look, that's exactly 4 times my original eigenvector. So either one of these are perfectly good choices, because really, when you're finding an eigenvector, I'm not sure what's going on there, but someone's having a good time. Felicity's brother, maybe, I don't know. Anyway, when you find an eigenvector, you're really finding a family of eigenvectors. So when you never have just one eigenvector, you have really an eigenline. So the whole, any multiple of this would be an eigenvector. So here really I'm thinking of like the entire x-axis being the eigenvector. Because it could be 1, 0, or 2, 0, or 3, right? Any of those fine. We usually pick the one that's nicest, which means the small, like it wouldn't pick 1/2 0, I wouldn't pick 3, 0. I pick 1, 0 because it's the nicest one. But really any choice is fine. Except for 0, 0. So back to what I was saying, when you're solving something like this and you get one variable equal to 0, that's an automatic, oh, I can pick the other one to be 1. There's no other work that has to be done, you're done. Let's go ahead and find the eigenvalue for lambda equal to 2. Sorry, the eigenvector for lambda equal to 2. Oh, we're almost out of time. Okay, well. So after we do this, next time we'll talk more about looking at the stability. I'm gonna try not to go too fast into it, but I also don't want to lag too far behind. So we'll try to hit the sweet spot there. For lambda equal to 2, it's the same equation, right? We're doing 4, 3, 0, 2 times the eigenvector we're looking for equal to 2 times the eigenvector we're looking for. Right? That's where the eigenvalue goes. That's that eigenvector. That's that eigenvector. And then we do the same thing. 4 times x plus 3 times y equals 2 times x. Most of the time, you should only ever have to use one of the equations. Right? I don't really need to write, in fact, it's not even helpful to write 0 times x, right? Here's the other equation, 0x plus 2y equals 2y. That literally tells me nothing. It tells me y equals y, which is true, but doesn't restrict me in any way, so I don't have any meaning from that. So you usually only have to use one equation, but sometimes one of them doesn't help you. But we could have just used this one and said, okay, well, let's see, 3y equals negative 2x. And once you get to this point here where you could divide both sides by negative 2, but you could also just pick x and y to be the opposite coefficients. And you can make x equal to 3 and y equal to negative 2. And that's what I actually would do. So that my vector is this vector here. You could also take the longer path and like solve for y and say, okay, y equals negative 2/3 x. But then I'm going to pick a number for x. I'm going to pick, not surprisingly, x equal to 3 because that's going to make my numbers nice. And then you get x equal to 3. Oh, y is negative 2. So there's one way to write the eigenvector. Okay, the quiz I wrote for you guys that's not due until like tomorrow night, is mostly about eigenvectors and eigenvalues, just so that you're comfortable with them. And yeah, we'll try and start talking about stability and equilibria on Wednesday. Again, if you have questions, don't hesitate to send them to me or start a discussion. I'm happy to make some short videos as well, because I know not everyone's in the same place. So if there's stuff that we've already passed by and you still need to see, just ask. There's the attendance again. I think there was one other thing I wanted to say. Nope, it escaped me. Oh well. If I think of it, I'll let you guys know. I'll see you all on Wednesday. Take care.
Thank you.
You're welcome.